Hi, in this video, we're going to have a look at transformations of quadratic functions. Now, you'll notice there's quite a bit of writing on these slides already, and we're going to explore what transformations mean, but these notes here are for you to, say, pause the video and write down, or wait for the notes to be put onto Google Classroom so that you can copy them into your summary books. But transformations of functions in general are all about considering what the base function is, and then applying different operations to the base function to get a brand new function. And these operations, or the applications of the operations, are called transformations. Now, as you can see here, what I've written is every quadratic function is basically the same. So we can transform or create a new function by applying operations to it. So the base function, which I have discussed before, and you're going to see some dodgy graph drawing now, is like this, isn't it? Okay, I'll put little arrows on it. I should be a little bit more sensible with my graphs, or with my axes, I should say. But that's the basic function, like so, the base function. So we apply transformations to the base function, and when we do so, we can create a brand new quadratic function. I won't say what those operations are yet, but let's just take it as an example of the drawing itself, like so. It is still a parabola, or it's supposed to be, but the parabola has flipped over. That's called a reflection. The parabola has shifted location, so it's gone from here to here, so it's shifted over to the left. And it's also, this is a bit hard to see, but I've also made it skinnier as well. But apart from that, it's still a quadratic function, and it has an axis of symmetry, and it has a turning point, just like all quadratic functions do. So they basically differ in these three things: size, reflection, and location. And reflection just means flipped upside down. Technically, you can reflect functions left to right as well, but because parabola functions or quadratic functions are always symmetrical, when you flip them this way, it just looks exactly the same. So we're just really interested in flipping this way. So it's gone from here to flip over here. Okay, so we're going to have a look at these in order, and I thought really the best way to see this in action is to play around with something like Desmos. So you can see here that I have got f of x equals x squared plus k as our first transformation. Now what you could do if you want to is you could pause the video and do this in Desmos before me, and then come back to the video to confirm what you are watching here, because it's the observations that are important. So what happens if I apply to the base graph of x squared a value k? And you can see underneath here, I've got k as a slider. At the moment it's 0, and it goes from -10 to +10. Okay, so when k is equal to 0, it's exactly the same, right? I've got x squared, and I've just added nothing to it. So it follows the base line here. But if I start shifting k, I'll pause now if you want to, and try this out yourself. Type in f of x equals x squared, type in f of x equals x squared plus k, and then when you do that, it'll say add slider for k. Click on add slider, and then you can play with it yourself. Okay, you've either paused or you just wanted to watch the video. I mean, that's fine either way. So as I shift the slider up here, have a look at what's happening. The parabola is going up the y-axis. It's going up. It kind of looks like it's shrinking, but it's not. If I zoom out, you'll see it's actually the same shape. It's just moved up ways. Okay, it's the same shape. And if I go down, so k is negative, I'm now going below the x-axis, so I'm traveling on the negative part of the y-axis. So basically, the graph doesn't change shape, it doesn't change left to right, it just changes top to bottom, like so. Okay, here's the next one. This one here is where I've taken away the value h and then squared the result. So I'll turn that one off. There's the base graph. just do that just so we can sort of see it a bit better. Now look at what happens when I move H this way. What do you think is going to happen to the graph? Pause, think about it, write it down. Oops, it would be useful if I actually turn the graph on. So there it is. So it's now, at the moment, H is equal to 0. So we've basically got f of x equals x squared. So that's why it's following the dots. But as I said, as I make H increase, it's going off to the right. Okay, but it is an identical graph. That's very clear to see now. It's an identical graph. It's just going off to the right. Notice I've got x minus h, and it's going to the right. If I go backwards, yep, it's going off to the left. Okay, so k makes it go up and down. H makes it go left and right, like so. Okay, so if I just sort of fill in some notes there, I'm looking at slide 14 there. So when we apply an operation to our base function, then so that it goes up and down or left and right, they're called translations. Translations are a change in location, but not a change in shape of the graph. I've tried to capture this as like a little function box here, but it is a bit tricky to get right. But you can see here the base function is f of x, that's x squared, and I've added k to it. So what that means is that as x is input, it is then processed, turned into x squared, and then k is added to the to that result. So that means that for every single point that goes into the function, the result is going to be just shifted up or down. Okay, so every point is shifted up or down by k. Now, I'm not going to write this down because I think it's pretty obvious, but write it down in your notes if you need to. If k is positive, then it will shift up. If k is negative, it'll shift down. Now, for the horizontal translation, the second thing we saw, what's happening here is that the h is being subtracted from x before the function is applied. So we take in a value, the value is then reduced by h, and then f is applied to x minus h. Okay, so the output effectively gets shifted across by whatever the value of h is, either left or right. Okay, it gets shifted across because basically if the value going in, let's just say for example, if the value going in is 10 and I'm shifting by 2, then the input of 10 is going to turn into an 8 here. 10 minus 2 is 8. And so we're looking at f of 8, which would be 8 squared, 64. So it's happening earlier. Yeah, if h was equal to 2. So everything is being translated or shifted. So let's just write that down. Every point is shifted left or right by the value of h. And again, it's worth putting a note in your summary book if you don't think you remember that if h is positive, it's going to go right, and if h is negative, it's going to go left. But note that it's x minus h, not x plus h. Okay, it's kind of almost counterintuitive to what you're thinking, which is why we write x minus h. But so if you had x squared, x plus 3 all squared, it's going to go to the left, not to the right. When we do some examples, you'll see that. Okay, the next thing to look at is dilations. Now, dilations, if I can just put this back to bed, there we go. So we'll look at dilations in all their glory. That's when we multiply f of x by a value. So let's see what happens. What do you think will happen? If I increase a up here, what's going to happen to the graph? Okay, feel free to explore and Desmos yourself. But as I increase a, the graph squishes. And you might think that's again counterintuitive. You think as a gets bigger, the graph would get bigger. That seems to be getting thinner. But what you need to think of it is like what it's doing is it's accelerating through the values faster. So whereas this has got a nice steady pace up here, this is going do 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 do. This one's going meow. So the bigger A is, the more meow it is. Okay, so the look of the graph is that it has got thinner. Okay, it has shrunk about the y-axis if you want to be technical about it. Okay, it's dilated to a thinner graph. Okay, because it's accelerating through those values faster. If I go the other way, down here, having a big negative number actually shrinks the graph as well, but you can see that the graph is now upside down. We'll talk about reflections in a second, but I just want to point that out. So the other useful point to look at is between 0 and 1. Between 0 and 1, you can see that the graph is a lot fatter. Okay, it is stretched. And it's for the same reason. It's basically slow-mode the graph, right? You're now traveling through the graph at 0.1 of the speed that you used to. So if this one's do, this one's it's slow mode down. Okay, it's still a symmetrical graph, it's still a parabola, but it has been slowed down. Okay, so that's what A does. Let's write a few notes about that very quickly. So as we apply A, so X, every point goes in, it then gets squared, and then the squared value either gets shrunk or stretched depending on the value of A. And it's a bit more tricky, so we're going to write that out a bit more precise. But so every point it's a bit tricky with dilation, so I'm going to say it a couple of different ways. Every point is closer or further away from the y-axis, with the exception, I guess, of 0, 0, i.e. the graph is shrunk or stretched. So that's how the graph is changed. The graph is shrunk or stretched because every point is either closer or further away from the y-axis. Okay, hope that makes sense. So we can probably finish this off yourself now, but I'll do it here. When A is greater than 1, the graph is shrunk. We say it's dilated towards the y-axis. And when A is, this just means between 0 and 1, i.e. that's a fraction. When A is between 0 and 1, the graph is stretched. So that's the summary of the dilation. And what does that mean? What do we call A? We call A the dilation factor. To be precise, I'm going to be more precise here, and you'll need to watch the video to know what this means. But the absolute value of A is called the dilation factor. So if A was negative 2.7, then the dilation factor would be 2.7. So I'll put that down. Hopefully that will make sense when you're reading the notes. So that's the dilation factor. So if you're asked to say what the dilation factor is, you just simply write down what A is without the positive or negative. Now, reflection is the last thing, and we've sort of already seen it. It's the simplest, really, and it's just that if A is below 0, then it's exactly the same graph as if it's above 0, but it's now opposite, like so. So if I just make A equal to -1, that's a dilation of, there we go, a dilation of the base graph exactly. So it's like you're looking in a mirror image here. Okay, so I'll just finish off those notes. F of x equals negative f of x, as you can see there. So sorry, x goes into f of x. So if it was the point 3, out would come 3 squared, which is 9, but then it becomes negative, and so every point becomes the opposite sign. So I'll be precise again. It's hard to get it really precise, but also succinct. But every y coordinate changes sign. Graph is flipped vertically. The technical term is it is reflected about the x-axis. It's reflected about the x-axis. Now we can put these things together. So if I have, you can see here I've put all of them together here. So if I show you what this looks like, I've got just my reflection here, a equals -1, but I could stretch it. I could then translate it across here, and I could translate it down here. And there we go. We've got our new quadratic function. And that's the whole point, that the quadratic function, that every single quadratic function can be turned into turning point form, this is called. You might remember that from your algebra unit. Since every quadratic function can be turned into turning point form, every single quadratic function is effectively just a whole series of transformations from the base graph, like so. And you'll note, this is the critical thing, I suppose, is that the turning, let me just pick some more sensible numbers. So k equals -2, h equals 3, and the turning point is 3, -2. And that should make sense if you think about it, because I said every point is translated. If on the base graph the turning point is 0, if I go down 2 and across 3, then the new turning point should be from 0, 0 to down 2 and across 3. So it's 3, -2. I hope that makes sense. I'll leave the video here, but in the next video, I will go through some examples of how to use this information to get critical information for sketching.